Hello everyone, my name is Christoph Reichenbach from Lund University, and I'd like to talk to you today about joint work with Hampus Balldin from Advenica in Malmö, who really did most of the hard work here, on a domain-specific language for filtering and application-level gateways. So imagine that you're running some sort of application server over the internet, then that means that you'll keep getting network packets over the internet, and some of these might cause trouble on your application server. Now this might be because someone's trying to attack you, or it might just be that some user is running an obsolete client or ill-configured client, or is pressing the wrong button somewhere. To prevent these kinds of issues, organizations often use firewalls to filter out problematic network packets. And these are effective at filtering by, let's say, IP address, but that's not that good if you have a legitimate client just happening to do something that you don't want. Now, to work with this, you have to work at the application level. That is, you have to understand in the OSI stack of network protocols at the highest possible level what's going on here. And there are systems out there nowadays that can do that. And these application level firewalls or gateways can reason about network packets on the level of, let's say, can the user actually download this particular file? Should this delete operation be allowed? And they can do things like strip out specific columns in an SQL Server reply to prevent sensitive data from going out over the network. There are different ways to implement these. One strategy that the ZoneGuard system by our supporting company Advenica uses is a pipeline infrastructure. And to understand this, I'm going to give an example based on the remote desktop protocol. This protocol, RDP, is used to control desktops over the network, and we might want to filter for different kinds of interactions here. If an RDP packet comes in, it gets processed by the input service, which translates the packet into a general purpose representation, think binary JSON format, which then is validated by a protocol validator that makes sure that we have the right structure, which passes it to the filter, which might, for instance, say that, well, I'm only allowing left mouse button clicks, so I'm going to strip out any mouse button clicks that I don't like. And then the filter would pass on the packet to the validator that makes sure that the filter hasn't done anything bad, passes it on to the service, and then it goes out through the network again. Now, if you want to build a pipeline like this, then you have to do a bit of plumbing for the service parts. The validators you can generate fairly simply from a schema specification, but nowadays at least, filters are still mostly built by, or always built by hand in a general purpose language. Our main contribution here is a domain-specific language that makes it easier to build these filters. And I've given you a short specification here in our language where we are checking that the button in an RDP packet is only within a list of allowed buttons. So if the button is not in that list, then our system is going to trigger a repair action, which is going to change the button number. And this repair action is going to make sure that the assertion holds. Now, in practice, these kinds of rules are written by a different team than the team that configures and deploys these kinds of filters. So we also have support for externalizing configuration. As part of this process, or elsewhere of course, it can happen that there are conflicts between the allowed operations and the repair actions. So in this case, someone who deployed the system changed the allowed buttons, but the repair action now repairs the button to a number that isn't actually allowed. And these kinds of conflicts can be difficult to diagnose and debug, and even find out that they even exist. And these kinds of pitfalls, therefore, can be difficult to find for developers. So the second contribution that we have is an approach for statically verifying that such a system has no pitfalls. We build our system on top of this pipeline architecture that you saw on the previous slide. And what we do is that we take a filter specification and configuration, and we synthesize a validator and a filter after checking and verifying with the help of an SMT solver that everything is okay. And this verification process makes sure that there are no pitfalls in the specification. And existing tools, of course, try to do some amount of pitfall checking already. For instance, Advenica uses the output validation approach, where every filter is always taking the output packets, passing it through another validator to make sure that the filter didn't do anything bad. So that's a form of dynamic checking. What we do instead is that we statically verify that no bad packet can ever be generated by the filter, so we are able to eliminate this extra output validation step. To understand a little better what we actually do, let's have a look at a slightly more detailed example. And here I'm assuming that we have a couple of thousand of sensors, and these send us, let's say, time series over humidity or brightness in whatever we're monitoring. Now, if we have a couple of thousand of these, then we're definitely going to get some garbage results from some of them. So we might want to filter out these garbage results. Here I've structured the data that we're getting into sensor data packets, which consist of either a single time series or a sequence of bounded time series. And we can see that as a sequence of bounded time series by this cleany star here. And a time series here is a sequence of values, so one or more value. And bounded time series is the composition of an integer that represents the maximum of that time series as well as the time series itself. So the total packet might look something like this: a sensor data node, then bounded time series underneath with the relative maxima that we allow for the values, and the actual time series with their values also attached to the bounded time series. So if we now want to express some sanity restrictions over all of this, we might, for instance, say that no value should exceed the maximum allowed by the bounded time series. And we express this in rules like the one that you see down here: bounded t-series .val less than or equal to bounded t-series .max. And the meaning of these names here, which we call path variables, is that they specify which attributes in the packet we are talking about. So bounded t-series .max, for instance, refers to any max attribute that is a direct child of a bounded t-series node. So that would be the max colon 127 on the left and the max colon -1 for the bounded t-series on the right. For the bounded t-series .val, this instead refers to any descendants of a bounded t-series. So these could be arbitrarily far down. So these two nodes here would be example of that. Now, if we have two or more different path variables with the same prefix in an assertion, then the semantics of our language guarantee that these are going to bind to the same node in the network packet. So that means that this rule that you see here is going to only compare maximum values and individual values within the same bounded t-series, because the bounded t-series part of this path variable is always going to be the same node for both of them. So here we're going to compare 4 against 127, -3 against 127, and then when we move over to the next max value, so -1 over here, we're only going to compare that against the values on the right-hand side time series. And here we actually see our first violation. So val here is greater than the maximum value, so clearly this is wrong. What our system is going to do with this specification is to reject this packet. Now we want perhaps to do some more fine-grained processing here. So what we might want to do instead is to filter out these problematic values. And we could do this by just overwriting them with the maximum values, or just clamping them to the max. And this would then lead us to putting this maximum value -1 into all of these val fields. So if we've done this, we have a valid packet that we can send on. And this would be an example of a perfectly fine filter that's allowed by our system. Now, if we go on, we might find that there are additional constraints that we might want to add. For instance, if we're measuring brightness and humidity, we might argue that the value should always be greater than or equal to 0. So we might add that as an additional constraint. And now we run into a problem, because this constraint actually conflicts with the constraint that we've imposed with the previous assertion. So this doesn't really give us a clear answer as to how we should repair this bounded time series. The first assertion requires us to set val to -1. The second one requires us to set it to 0. So we detect these kinds of conflicts statically, we call them subverted repair, and report them to the user and disallow these kinds of filter specifications from ever being run. The user can now go in and try to fix this. For instance, the user might now say that, oh, well, obviously the problem here is that a maximum value should also never be less than 0. So if the user adds this additional assertion, then our system is able to utilize the connection between these different assertions to formally verify that the bounded time series that come out as a result of this filter specification are going to be well formed. So our system is going to be happy with this specification and is going to let it run, since the last specification makes sure that we don't run into the pitfall that we saw earlier. So I hope that gives you some idea of how the language works. Overall, our language is declarative. It uses assertions of positive properties rather than checks for properties that should not be the case, because we found that that works better. Most of the properties we wanted to write down were of this positive form. It is also statically typed based on a number of primitive types, constraint types, multiplicities, variants, and non-recursive structures. We haven't yet found a use for recursive structures. We don't think there's a fundamental problem with them, though. And assertions using the usual arithmetic and string comparisons, including regular expression matching, as well as the path variables that I showed you earlier. These path variables we can also reify into lists, and we also support list comprehension and list aggregation. Now, there are some limitations here. We mostly in practice use comprehension and aggregation for configuration, and our verification system is still quite conservative when dealing with lists of nodes, since we haven't really found them to be that important for our filters yet. To repair packets, we allow discarding packets, removing subtrees, updating elements, plus some reporting operations. We also support multipass filtering, which can be useful if, for instance, you have one pass that removes problematic elements and another one that removes empty structures to clean up afterwards, or one that has rules of different priorities. And of course, the main part of our language is to statically verify that the filters lack various kinds of pitfalls. So I'm going to do a brief overview over those kinds of pitfalls. We disallow impossible assertions or vacuous assertions. We make sure that we can never invalidate the schema. Our language design is not Turing complete, so we don't enable any termination bugs. We check for runtime faults, specifically division by zero, and we prevent ineffective repairs, that is, repairs that do not in a single step make the assertion of the rule true, as well as repairs that interfere with each other, so subverted repairs as we saw earlier. For that, we use a sub-Turing complete language design, general type and multiplicity inference, and a verification approach based on SMT solving. Now, in the interest of time, I'm not going to show you in too much detail how the verification process works, just to point out briefly that our system is able to extract while verifying not only counterexamples, but also different kinds of lemmas from existing assertions that it can then use to prove other assertions later on, especially when these run one after each other. So with that in mind, we support verification. We also have limited support for validation through a mechanism that allows us to synthesize example packets. I'm not going to go into that into too much detail. To evaluate our approach, what we did was to sit down and re-implement several filters that Advenica ZoneGuard system already supports. So the first author did all of this work, taking these filters. Here you see the lines of code of the original filters minus some boilerplate code. And we found that after translating them to our system, they were substantially smaller, both with respect to lines of code and with respect to numbers of tokens, especially as far as the filtering rules are concerned. Now, for the schema rules, which make up a smaller proportion, a third or less of the specification, we found one instance where we needed more tokens but fewer lines of code, but we don't consider this to be problematic. Our checks run relatively quickly too, so the user can get feedback in a second or less, even for the more complicated kinds of filters running through the SMT checker. We also ran a case study on all of this, and for this case study we selected a filter engineer from Advenica who had previously implemented a filter in the ZoneGuard system, and we asked that engineer to re-implement that same filter in our system after giving them a tutorial. And the engineer was successful in implementing that with minimal help from the first author of this paper, who just answered some simple questions. Then the engineer filled out a questionnaire, and the second author interviewed the engineer over the phone. And we found overall that based on the engineer's feedback, that the strengths of the language were largely where we hoped they would be. So we have a good closeness of mapping to the problem domain, and we're able to relatively easily add more filters and understand them and modify them. But we were somewhat limited in that the developer always has to specify the schema specification first and can't really experiment very well due to our strong verification approach. Now, we're not sure if we need to actually solve that. There's some other hurdles that we're concerned about, which are the learning barrier or learning curve for new users due to a number of unusual language features that we have, as well as the limited expressivity and challenges that are fairly practical, such as DSL maintenance. So overall, we have introduced a declarative domain-specific language for application-level network filtering that is able to verify the absence of a number of known pitfalls in this kind of filter specification. And we've shown that this language is effective for a number of realistic filters, and found a number of interesting pieces of information that show us that the language is useful for existing filter engineers, but has some challenges to adoption that we still need to think about. So with that, I thank you very much for your time and interest, and please let me know if you have any questions.